Section 4.6 is velocity and acceleration. This is velocity and acceleration in uniform circular motion. So I'll again draw for you the trajectory of the particle. So we look at the particle in uniform circular motion below. So I'll read, actually let me draw the circular part. So we have something like that. And we can think of this as one trajectory, as one velocity, and that's another. So this is V, and that's V. Okay, so the radius is R. And so we know that a change in velocity can be found. So we've done something like this before, so we won't redo it here. But if you think of the change in velocity vector, you may think of it, actually let me redo this, hold on. The change in velocity vector points this way, so the acceleration is down that way to the center of the circular path. And so you consider that the velocity of the particle is this way, the acceleration is to the center of the circular path. So in order to find, at least I can show you how to calculate this acceleration just by working in the XY plane. So suppose we have a particle moving along a circular path in the XY plane like that, just like we did before. Okay, so it's moving along like that. So this is a velocity V, and that's a velocity V. And we can think of the displacement. This is delta theta, this is R. So if you think of it this way, then we can say that the change in velocity vector will be a vector which points this way. So this is the change in velocity vector, delta V. Okay, so this is V, and that's V. So this angle is again delta theta. Okay, so this, I've just taken away the change in velocity from here and I've put it here. So basically what we have would be two similar triangles. So let's think of the velocity vector V subscript t as a vector at a tangent to the circle or to the circular path. So V subscript t is at a tangent to the circular path. So if we go back to this drawing again, suppose we can think of V subscript t, and here is your acceleration A again, and the length of the arc here of course is S. This angle is theta, we can use theta if we want, and this is R. So we know S is equal to R theta, and if you like you can say ds dt is equal to R d theta dt. Okay, so this is the length of the arc of the circle, and so ds dt is equal to the tangential velocity V subscript t. And so V subscript t is equal to R d theta dt, where d theta dt is equal to omega. So we saw that once already, that d theta dt is omega. So we can say that the velocity tangent to the circle is equal to R omega, where omega is the angular velocity of the particle in that path, in that circular path. So this formula gives us a relationship between the linear velocity, which is at a tangent to the circular path, and the angular velocity omega, which is the velocity of the angular velocity of the particle in its circular orbit. And R is just the radius, or you can think of it as a distance from the origin to the point where the particle is located. So let's look next at the acceleration and see if we can get a relationship here for acceleration, or the centripetal acceleration A. So this is the acceleration that I've shown you for the object moving in a circular path. A is the acceleration vector pointing to the center. So I'll show you the A again. So if you have in the XY system again, we have the particle moving from one position to another. The A is the acceleration that points here, and this would be a velocity V final. This can be a velocity V initial. So A is the acceleration vector that points that way. Okay. If you think of taking that that graph out, we can draw the positions this way, where this is the angular displacement delta theta, and if you think of it, then you will see that this is R, and so we can have, for example, this is R and this is our S, like that. We can do the same thing for the velocities, a final velocity and an initial velocity, and this the displacement or the change in velocity is delta v, which goes that way. So this is v and that's v. So this angle is delta theta also. So what we are doing is just showing you the similar triangles involved. Let's put a vector on it to distinguish it from r, which is this one here. So these are radius r. Let me rewrite them so they look like r's. So we are just trying to create a similar situation for you to see. So this is S. So if you make this delta R, yeah, so this delta R is the difference between the two position vectors that are shown there. So we can say that using the similar triangles for delta R is also a vector, and delta V, we shall see that delta V over V is equal to delta R over R, and we're talking of magnitude of those two. Delta V over V is equal to delta R over R. So delta V will be equal to V over R delta R. So if we wanted to find acceleration A, acceleration is our change in velocity with respect to time, which would then be equal to V over R delta R over delta T. And we shall say that as we make delta T approach 0, delta R over delta T approaches V, or becomes equal to velocity V. And so we can say that the acceleration A is equal to V over R times V, which is just V squared over R. So A is equal to V squared over R, and this is the centripetal acceleration, or acceleration to the center of the circular path. This is centripetal acceleration. Since we also know that V is equal to R omega, we can write the centripetal acceleration as R omega squared over R, which gives us A equals omega squared R. So we can say A is equal to omega squared R. So that's just another way of writing centripetal acceleration. Any questions on that?